morning, good afternoon, and good evening, everyone. In this part of the machine learning series, I, your host, Asha Danwa, will take you through an explanation of the random forests. So, first of all, we are going to start with what is machine learning, and then what is random forests, and what is so great about random forests. But before we learn about random forests, we have to learn about what is the ensemble method, and what is classification, and what is a decision tree. So let's go through those. And starting off with machine learning. So basically, machine learning is programming computers to optimize a performance criterion using example data or past experiences. So, for example, we will be training the certain model given a training data set, and this data set may have classification. We might have to put little tags on them, and therefore we can easily interpret them. Or on the other hand, we can be without any tags, and then it is up to the machine learning algorithm to interpret and manage those results. So that is called unsupervised learning, and when we do add tags is called supervised learning. So the main point here in machine learning is that there is no single solution that can fit it all. That is the whole point of supervised and unsupervised learning. So the key point is, however, that the algorithm gets better the more data it has. And the best example I can tell you of this is, have you noticed how when in the captchas they keep getting harder? So it used to be a simple checkbox, then text, and now we have to select images from a selection of that's put forward to us. So what do we need to understand about random forests? We need a few things. First is the decision trees, the classifiers, and the ensembling. So let's go through each of those. So, but now before we learn about forests, we have to learn about the trees in the forest, the trees that make up the forest. So there is other good videos on the exact that go into much more details on the decision trees, and in this very channel. So I urge you to go check that out. But to summarize, decision trees are the building blocks of the random forest model. So they work by asking a simple yes or no type question about the classifiers applied to a sample. And what is a classifier, you ask? That we will be seeing in the next section. But after this classifiers are applied to the sample, one after the other in section, until the data is sorted, they are sorted into the most pure form. So in the example shown, if our data set is consisting of just the numbers shown, some are red, some are blue, and some are underlined. So what we want is the underlined, separate the underlined red numbers. So what's the first question we have to classify? The first classifier, it's red. So is it red, yes or no? Then ones that are red, is it underlined or is it not? And thus we arrive at a conclusion or a result. So this is one single decision tree, and each split is called a branch. So what a random forest is, we will come to know, and this is very important to that end. So next up is classifiers. So a classifier is a machine learning algorithm that automatically orders or categorizes the data to one or more set of classes. Classes is based in basically it is a tag or a type of data that we can easily put, like a say container. Like for example, we could say for example, a class of data can be red or blue, or it could be underlined or not. A classification algorithm sorts that, right? So there are both unsupervised and supervised classifiers. Unsupervised machine learning classifiers are only unlabeled, have only unlabeled data sets. Are only fed unlabeled data sets, which they classify according to pattern recognition or structures and anomalies in the data. Supervised, on the other hand, are fed training data sets which do have tags, and that trains them to identify a particular category of data and do so very efficiently. So has anyone, if anyone has used the apps like Grammarly, they can tell if our SM is by the text in the words we use, the text, the structure we use, is it positive, is it neutral, or is it negative. So this sentiment analysis also is a type of classifiers. It's a type of supervised classifiers, and it is an example where machine learning, where classifiers are trained to analyze text for opinion and for a certain type of bias. So next up, the last of the three categories we need to know before getting into random forest is ensembling. Well, basically what ensembling attempts to do is, we have many models. So as you can see the diagram, how can we increase the accuracy while also decreasing the cost of storing the data, training the models, and maintaining the various models. So it basically, as you can see in the diagram, the solution it more or less proposes is grouping. So how can you increase the accuracy? How can we group together models? And how can we reduce the cost and all those good stuff. So what random forest is an ensembling applied to decision trees view with classifiers. So an ensemble model with decision trees and classifiers. So where does this cheat sheet actually applies to many other machine learning models, but let's just focus on the random forest one. So from the it's like a game. So from the start, the dimension reduction, label data, no dimension reduction, yes to label data, and we can either go with no or yes for predicting numerics. That will become important. So what does this mean? Random forests are a form of supervised machine learning algorithm specialized around large data sets of numeric data, or not. It can be go either way, and it can also, therefore it can be used as a classification as well as regression. That's basically what it means. So this diagram shows the main concept of the random forest. We start in the previous sections, we figured out what a decision tree is and how a decision tree works. Basically what the random forest does is, it takes multiple decision trees. Not when I say multiple, I mean like thousands and thousands and possibly thousands of decision trees, and it if it's a numerical data for regression, it averages it, or it takes the most common value. If it's the case, in the case of classification, it takes the most common agreed upon value. So that is how it arrives at a consensus. It builds multiple decision trees and merges them together to get a more accurate and stable prediction. So the random forest adds additional randomness to the model while growing the trees, and instead of searching for the most important feature while splitting the node, it searches for the best feature among a random set of features. The result is a widely diverse and generally diverse result, and it generally results in a better model. So what does this all mean in English? So imagine you ask your friends and family about going out to eat. A child would, your small cousin would give me a recommendation, let's go to McDonald's. About they will be basing it, thinking that you might like I don't know, burgers and fries and like stuff like that. Your parents, your mother, she will be asking, why do you want to go out? When was the last you have not been eating health? She will be concerned about your health, about what you've been eating. If you ask your friend, he might be thinking, what was the last time what was the last place we went to eat together? How many times have we gone there? Should we try something new? And if you ask these days, if you try to go and ask a PHI of that, he'll be asking, what are you thinking about going out to eat in during this COVID situation? Uh, the point is, the answers are all based on different criteria on what that person thinks should be with best aid in the decision of where to go to eat. And in this case, I think most of them will be pointing to go eat at home. So in random forests, what the very very important thing is, has to be random. So what does that mean? The randomness in the random algorithm means the correlation between the trees has to be very very low. So uncorrelated models can produce predictions that are more accurate and then the individual trees in the forest. And the reason for this is that because the trees, when they are brought together, they can perform a sort of check, and they can look at one and say, hey, this is not right, I'm going to do my own thing, I think this is right. So when there is a unfiltered and we can say dirty data, they don't let it propagate. So because it is a consensus, there's a lower chance that such impurities will be in the end result. So there are three main methods of ensuring randomness. First is bootstrapping, next is bagging, and next is feature randomness. So bootstrapping is essentially means dividing the data set into smaller random chunks. For example, if there are 10 elements in the data set, there we could have, like, say, elements of 4 each, and each of those elements will be a random set. The point is, it is smaller than the total data set, but it is nevertheless random. Next is bagging. Basically, bagging is, as you can see on the slide, it's bootstrap aggregation. So if, for example, in the previous example, we take the set of A, B, C, D, and E. In bagging, what we would use, we would introduce a random variable such that each data set, when we create each set, it is the same number of variables as the original data set, but it has randomly placed spaces, if you will, so that each set again is unique. This is a second option of ensuring randomness. So what is the next option? Next option is feature randomness. So basically, we in our previous example, we are going to eat. So one would have been where did we eat last? Were we eating healthy? Do I like biryani or do I like burgers? So those could be several features. So in a decision tree, each feature will be analyzed against each other in sequence, and to arrive at a optimal result. In a random forest tree, we would select. We are not to ensure the randomness. Each tree in a random forest can pick only from a random subset of the features. That is, if there are 4 features, as you can see, we can only pick maybe 2, maybe 3, like that, but not the whole set. And each subsequent tree will be a random combination of these sets. So in combination with the bootstrapping or the bagging, so this is almost guaranteed to produce random trees, so that no two trees have the same output, and therefore it increases the efficiency and the accuracy of the algorithm. Right. So that's it for the what is in the random forest. So what's so great about it? Why do we need what's so useful about the random forest algorithms? It is versatile. So it can be used in both the, as you can see, the regression for analysis of numeric data and for classification tasks, for analysis of classifiers such as red or blue, male or female, something like that. So I've said it before, random forests are a form of supervised machine learning algorithms specialized around large data sets of numeric data, and it can be used as with classification as well as regression. So in a lone decision tree, you can trace up from the results, the root up to the top. So for example, the end result, you can go up the branches and arrive all the way up to the origin. So this is easy for us to understand, to trace back, but it is not very accurate. The random forest, on the other hand, shows together many decision trees. So, and because of that, as we discussed earlier, it is very, very accurate. But because it is a whole mix of so many trees and a common average result, you cannot trace it back. So this is not a bad thing, but it is something for consideration when and where we want to apply the random forest. And another point of consideration on when and where to apply the random forest is its main limitation. So the main limitation here is that it is very thorough, and because it is very thorough, it is very slow, and therefore it is not suited for where we want a quick response with for a real-time application. So random forests are typically not suitable for such applications. So when we talk about what's so great, we also have to be careful of what we should be doing to ensure that what the random forest needs for it to be as great as it is, or not so great for what it is. That is to say, we need features that have at least some predictability. So the algorithm is not flawless. We have to be careful of primarily to apart from what we discussed in the previous sections. We have to be careful of at least these two features. So the features must have at least some predictive power, and the trees of the forest have to be uncorrelated, and their prediction need to be basically their predictions need to be uncorrelated, or at the very least have low correlation with each other. The higher the correlation, the lower the accuracy. So inversely proportional, the correlation level of correlation is inversely proportional to the accuracy. And while the algorithm itself via feature randomness tries to engineer these correlations as low as possible, the features and parameters we choose will impact these ultimate correlations. So we have a whole load of things that we need to be careful of. With that, I conclude this small window into the random forest algorithm. I hope you gained some insights from this session, and I hope you can apply this, and I hope let's have a lively discussion perhaps in the comment section below. So anyway, have a nice day.